Hi, sir. We can start.
Okay, good.
Okay. Shall we, sir? Okay. Shall we start?
Yeah. So let's start.
So let me have a small introduction. Then I will hand over the session to you.
Yeah. Thank you.
Okay, sir. So good morning, participants. Probably here it is good afternoon for us, and it's morning for our speaker. And on behalf of Department of Physics, SNS College of Technology, I welcome you all for this international webinar on the topic binary nanoclusters produced from cluster beam source for heterogeneous catalysis. So this session would be an eye-opener for us in this new area. And I also welcome our resource person, Dr. Yubio New, for accepting our invitation. And it gives me immense pleasure to introduce our resource person. So he is a research officer at the College of Engineering, Swansea University, UK. And Dr. Neo is having expertise in material characterization, nanomaterials synthesis, and thin film technology. He has published many research articles, particularly in energy storage devices. With this few words, I would like to hand over the session to Dr. New. Let us all listen his words. Thank you. Thank you all.
Thank you, and good afternoon, everyone. Thanks for the invitation and the organization for this webinar. It's my great honor to give this talk. So the title of this talk is Binary Clusters Produced from Cluster Beam Source for Heterogeneous Catalysis. So I'm Yu Niu from Swansea University, working in the same group with Richard Palmer. So at the bottom, you can see this is the campus that we are working on at. So you just like 2 or 3 minutes walk to the sea. So on the right, this is the city center of Swansea. Basically, the university is a bit outside of the city center, but they are all around the sea. So it's a nice place to work. Hope you can have a chance to visit us in the future. So let's go back to the talk. So this is very brief history of nanotechnology and cluster science. So people may call them cluster or nanoparticles. Basically, cluster nanoparticles with a diameter less than 10 nanometer or 5 nanometer, just few thousand atoms in the particle. We call it cluster. So it generally agreed that the concept of nanotechnology began from the famous lecture, which is there's plenty of room at the bottom. TEM, so we have a better characterization for nanoparticle. This make cluster science develop a lot. And then the reason that cluster science is interesting is because of the surface area to bulk ratio and the electronic band structure of the nanocluster. And then people trying to bridge the gap between the atomic and the bulk properties, and this becomes dramatically interesting during that time and even now. So today I'm going to talk the cluster or nanoparticle produced with the cluster beam deposition technique. So basically it's a physical technique compared to the chemical method. So we don't use solvent and the ligands around the particle. So this is the one of the class source we use to produce nanoparticle. So this one is used to produce size-selected particle because it has a mass field. So basically it has 4 sections. In the first one, we call it a generation chamber. So this is where the magnetron sputtering and the gas condensation happens. So basically this is a class source based on magnetron sputtering, which is quite widely used technique. So you have your metal target mounted on this magnetron head, and then you start the sputtering with argon gas or argon plasma, and then you introduce cool helium in the chamber. So the atoms or class Cs from the sputtering become larger and larger. So then those clusters go to the second chamber, which is the ion optics. So in this chamber, we just extract the cluster beam, the center part of the cluster beam, and focus it into the mass field, which is the third section called mass selection. So in this one, we use lateral time of flight mass field. So basically, you have 4 plates. So from bottom 1, 2, 3, 4, you have a section open in the middle. So for plate 2 and 3. So when the cluster beam goes into the mass field, you generate a pulse. So give the cluster beam a vertical momentum. So then the particle goes up to this section, and then you give it another momentum, which is opposite to the one you just gave. And then you just slow down the nanoparticle vertically, but it doesn't change the horizontal momentum. And then the cluster with the specific size will pass through this mass field and go into the 4th section, which is the deposition chamber. So with this class source, you can create nanoparticle below 10 nanometer. You can generate single atom cluster beam. You can tune the size of the cluster by tuning the gas flow, like argon and the helium in the first chamber, and then you can change the sputtering power, and basically you change the amount of atom in the generation chamber. Then you change the aggregation process. Then you just tune the isomers to different size. So with this one, we have a mass resolution of about up to 130. That means, for example, if you produce a cluster with 130 AMU, the error bar would be minus +1. So, but normally we just use like a resolution of 20 because this will increase the current, basically the population of the cluster. If you use the 130, the current will be very, very small. It takes longer time to deposit. So I'll give you 2 examples basically for the catalysis. The first one is used in the electrochemistry, which is a hydrogen evolution reaction. It is a half reaction of the water splitting. And here we use MOS2, which is quite popular material back a few years ago. So the MOS2 has a sandwich structure you can see in the picture with the moly atom in the middle and 2 layers of sulfur atoms up and the bottom. The other reactions or the other materials we use is gold and gold titanium for CO oxidation. This is very simple but very important reaction in the heterogeneous catalysis. So let's go to the first one. So let's come to the MOS2. on the left, there's a volcano plot showing the hydrogen evolution reaction activity of different materials. So basically, you want a material with the adsorption free energy as close to zero as possible, so the hydrogen can be adsorbed and deadsorbed freely, which is good for the reaction. But at the meantime, you want higher exchange current density. So that's how this plot comes from. So basically, at the moment, the platinum is the best catalyst for this reaction, and but the problem with platinum is expensive and scarce. So people are trying to look different material to replace platinum or deduce or decrease the amount of platinum in the catalyst. So in here we select MOS2, which has very low free energy of hydrogen adsorption, but the problem is the activity is not as good as platinum. So we're trying to increase the activity of pure MOS2 to shift the position of MOS2 upward a bit. So here is the crystalline MOS2. It has two edges, which is sulfur edge and the moly edge. So basically, in the MOS2, the only active site is the sulfur. So for example, on the moly edge, there's only one sulfur attached to the one moly atom, but on the sulfur edge, there are two sulfur atoms attached to one moly atoms. So basically, on the sulfur edge, there's more sulfur atoms. But at the moment, it's only the moly edge is active because because it has a moderate hydrogen adsorption energy. But for the sulfur edge, I think let me think. Yeah, I think I just made the mistake. I think that only the sulfur edge is active. So the things, if you dope the moly edge, you can make the moly edge active as well. So you have both edges active for this reaction, so you can increase the activity. Because we're trying to dope the MOS2 material, so we need another magnetrons. So we use this dual magnetron sputtering technique. Basically, you have MOS2 mount in one head, and you have another materials like nickel, cobalt, iron. So we tried nickel and cobalt in this reaction, but here we I'll just show you the nickel. So basically, you spot those two materials together, and then you get if you control the power on each target, so you can control the amount of say nickel in the MOS2. So this is the on the left. This is the stem image, the TM image of the MOS2 comes from the dual magnetron class source. For the pure MOS2, so you just switch on one target with the MOS2. So then you get the cluster like this. Come back. And then in the middle, you have nickel plus MOS2, so nickel doped MOS2. We also made pure nickel. So for the from the image, you can tell that nickel is crystalline, and both MOS2 and the nickel doped MOS2 are amorphous. So we tested the hydrogen evolution reaction for all those three materials. On the right-hand side, you have the LSV, so linear swap Watanabe of this reaction. So basically, what we found is that the nickel-doped MOS2 has enhanced activity by shifting the unsent potassium, about 100 milliwatts, which is good, but not as good as we expected. So we realized that the problem might be the crystalline of the cluster. So basically, all these theoretical calculations based on the crystalline of MS2, but what we made is amorphous or polycrystalline. So we did another thing. So we just add one more chamber to the class source. So after deposition, we just add extra sulfur onto the cluster. So we made the cluster crystalline, and then we test the activity again. So from the left bottom, you can see this is the cluster after, this is the size selected one. So it has 1,000 units of MS2, but basically they are polycrystalline. So, but they have layered structure showing from the stem intensity, line intensity profile. It has from the diameter distribution, you can see there are two peaks. One is around 3.8 nanometer. The other one is 5.5 nanometer. So that means during the formation process, basically the big cluster may comes from the small cluster connected to each other, but they may break down after deposition. So after sulfur addition, on the right-hand side, these are the images showing the after the sulfur addition and the annealing. So from the diameter distribution, you can see there's only one peak left, which is around 6 nanometer. So basically, this comes from the peak of 5.5 on the left-hand side. So when you give the extra sulfur into the cluster becomes bigger, and they connect the breakdown cluster into one cluster. So they just rejoined the from the both from the image and the FFT, you can tell that the cluster are crystalline, and they have a layered structure as well. So, which is good. So the next step is just we are going to test the electrochemical activity to see the improvement. So here comes to the HER measurement. From we test basically we test the different materials, which is pure MS2 and MS2 plus sulfur, and we test different coverage. We tested 5% surface coverage, which means that 5% of the surface is covered by the cluster, and on the figure B, it's 20% of the surface area is covered by the cluster. And from both A and B, you can see there's significant improvement regarding the unsent potassium. For the 5% one, you have 180 milliwatts saved, and for the 20%, you have 220 milliwatts. And the thing is, if you calculate the exchange current density, so basically you have like, compared with the pure MS2, the nickel doped MS2 has exchange current density 30 times higher than the pure MOS2. So basically, we found that the crystalline help to improve the electrocatalytic activity, and the sulfur addition help as well. So this is what we found with these clusters. And then we did cobalt, but it's not showing here. So I'll just give you another example of gold particle for CO oxidation. So it has been widely known that gold is very good catalyst for CO oxidation. So, but the problem, if you look at the graph on the left, and the substrate we choose is silicon dioxide, the green one. So basically, there's no activity on this substrate, regardless the size. But for other sports, you got very good catalytic activity when the size below 5 nanometer. So gold is a very good example of size effect in catalysis. The problem is during the reaction is the centering. So the small gold particle may center with each other and become bigger. Then basically you just lose the activity. So they are not active anymore. You can't reduce the size because it's not reversible. So the idea here is we alloy the gold with the titanium, and we studied the centering process of those two kind of materials. On the left is the stem image of the pure gold nanoparticle with around 4 nanometer. It's size selected gold nanoparticle, which it is gold 2057. So which is a magic number as well. And then in the gold titanium, we use the similar mass. So you can see after deposition there's already centering, which comes from the overlap of the particle during the deposition. So basically one particle located on the other one, then they just become one particle during the deposition process. So this is what we are not interested in, but so it happens there. And then we use stem. So basically we just send electrons to the particles. So we choose those two kind of particle where they are close to each other, and just call them dimer. So under the electron beam irradiation, the gold particle just comes together and they become one particle quite quickly, like after 30 minutes here. The gold particle become one particle, and then comes to the gold titanium. So the centering process is really slow, and it shows a different centering mechanism compared with the gold. In the gold, basically the big particle just moves around and find each other and then join each other and become one particle. In the case of gold titanium, there's atom diffusion at the beginning. So the diffused atoms build a bridge in the between, and then this bridge can just drive those two clusters moving together, moving towards each other, then joined together, become a particle, but it's still two particle, but with a connection in between of 30 minutes. So here we show that if you put titanium in gold particle, you just slow down the centering process. So this is the case with 0.3 or 0.25 nanometer gap in between. So then we studied the nanoparticle with a larger gap. So this is gold particle with 0.75 nanometer in between. So you can see after 30 minutes, they can still move around and become one particle. In the case of gold titanium, you can see even after 30 minutes, there are still two particles with a gap in between. But what happened during this process is they just exchange atoms in between. So from the zoom in image, you can see there's a few single atom in between. So basically those atoms just jump around and adopted by the big particle. here's another case. Basically, those two particles are already connected with each other before you're doing the electron irradiation. So for the gold, there's no surprise; they just become one particle. For gold titanium, even after 30 minutes, there's atom diffusing, but the particle trying to hold their positions and trying to against the centering. So we found that the gold titanium cluster show a strong anchor effect against centering. Regarding the seal oxidation activity, we found that this is very first test. So we found that the gold titanium is active for the seal oxidation, but gold shows no activity because it's on the silicon dioxide support. There's a support effect as well. So, but this is the very first result, so I didn't put it here. This is still ongoing. So the reason that gold titanium has an anchor effect explained by the DFT calculations. So basically, if you alloy titanium with the gold on silicon dioxide or silicon oxide surface, the energy of those particles with the surface become quite different. So basically, the titanium in the gold titanium cluster can establish a bond with the surface oxygen. So this is where the anchor effect comes from. This increase the absorption energy of the particle, make them stay in their position to against centering. And so this is the other source we use to produce nanoparticle, which is called laser ablation class beam source. So it's quite simple. So instead of use magnetron sputtering, you use a laser to hit the target. So you have your target. It can be single metal or it can be alloy. So you just hit it up, and then you generate atoms in the chamber. Meanwhile, we introduce helium as well. So there's a condensation process. So the small cluster can become bigger, and then you go into another chamber which is similar with eye optics, which is called extraction chamber. So you just extract the beam into the deposition chamber. Instead of use, so this is not the mass selected cluster or size selected cluster. Here we use reflectron time of flight to monitor the size of the cluster we produced, but we don't use this field to do deposition. So basically, all the particles are non-size selected here. What we did is we did platinum nickel alloy cluster for methanol decomposition, which is very important reaction in the fuel cells. So basically, platinum is widely used in this reaction, but the problem is it can be poisoned by the CO produced from the reaction. So basically, you decompose the methanol into CO and hydrogen, but the CO can poison the catalyst. That's the main problem. So here, we produced platinum nickel with 5 different compositions. You can, from the top, you can see there's PT 0.9, nickel 0.1, and all the way to platinum 0.1, nickel 0.9. So on the left bottom, you can see these are 3 examples of high magnification STEM image. On the platinum-rich cluster, so you can see there's a more the structure is more like pure platinum, but you have like some tiny core with nickel-rich area or domains. For the 5051, which is in the middle, so you have kind of very well alloyed structure, but you can still see some small domains, which is with the nickel rich area. The nickel rich cluster, so in figure C, you can see they formed kind of core shell structure with the platinum rich core and basically nickel in the shell, and the nickel is the shell is extend to a larger area because of the oxidation. So you basically get a nickel oxide shell, and the shell become larger and larger if you put it in the air for a longer time. But for all those 5 computations, we got average diameter around 2 nanometer. So we tested this particle for methanol decomposition. So we also use STEM EDS and XPS to prove that we got alloy cluster instead of the random single metal cluster. We found that in the cluster, the platinum is occupied by the metallic atom, but for nickel, they get